Good morning. I hope all is fine. Any questions? Okay, so I'll just put down our procedure here again. We have this time-dependent Schrödinger equation, which we separate out into two pieces. Okay, so T of t and u of x. And the way we do that is T of t is equal to e to the minus I et over h bar, and u of x is a solution to the time-independent Schrödinger equation. Hu is equal to eu. So the results depend on e, so we put subscripts on all of these things, indicating that okay, everything there is going to be a function of e. Okay, and once we obtain these things, we decided that, for example, if we had a bound state, the levels would be discrete. If we have scattering states, then E is a continuum. But in any case, we start with some general expansion of the initial condition. So psi x0 is given, and that we are going to expand in terms of some series, okay, so which runs on possible energies, and e of x. And once we do this expansion, then what we have for psi xt is sort of trivial. We have e ce ue of x, and the time dependence e to the minus I e t over h bar. Okay, and okay, so for example, you have homework which is associated with expanding a given initial condition in terms of the infinite well eigenfunctions. Okay, I'll do just one extra application of this before we move on to some other type of potential. So again, as an example, suppose I have this infinite well. This time I'm going to put it so that it extends from minus a over 2 to a over 2. Okay, so those are my potential walls. Okay, so the particle is excluded from places where potential is equal to infinity, and I have v equal to 0 in the center. Okay, so if I want to write this out, I would say v of x, so this is the x-axis, this is our v of x, is equal to 0 for x magnitude less than a over 2, infinity otherwise. So this is still our same problem, okay, same well that we discussed earlier, but this time, okay, I have moved the well to the origin. Now, the way we did it before with the well between 0 and a has the advantage that all of the eigenfunctions can be written in terms of sine functions. But here, when I try to put down the eigenfunctions, you see that not all of them will be signed. The eigenfunctions will be the same, except that I have to write them now in this coordinate system. Okay, so this is, I'm going to plot the u of x's now. So u1 of x will look something like this. So you see, it's not a sine function, it's a cosine function, right? It's the same function, okay? The functions that we did for, so let me just put that over here also, 0 to a is the same function, okay, in terms of the functionality, but the function that I used here was sine, okay, n pi over a x, which covered all of these things, okay? So I had these functions, all of which can be expressed as a sine function because the function goes to 0 at x equal to 0. However, in this case, you see that at least for some of these functions, I'm going to get cosines, and for some others I'm going to get, okay, I'm going to get sines and cosines depending on what I have. Okay, so functions, the first one, for example, is going to be what? Cosine, right? It's going to be pi over a again, x. So the k part, okay, the part which represents the wavelength doesn't change. But now this has to go to 0 at plus or minus a over 2. So I need cosine pi a over 2. The second one is now going to be a sine function. By the way, I also had normalization for these things, right? What was that? 2 over a, right? That doesn't change. So sine 2 pi over a x for u2. So you can, again, check that this goes to 0 at plus or minus a over 2. But now this also goes to 0 at the origin. So I have all of these objects, so the general form is going to be un of x will be equal to either square root of 2 over a cosine n pi over a x for odd n, or it's going to be 2 over a sine n pi over a x for even n. Now the advantage of putting the box symmetrically on the x-axis is that now you can use these symmetry arguments when you are doing integrals and such things, okay? So depending on which placement of the x-axis is more convenient for you, okay? You can use one or the other, yes.
We wrote differently, sin 2 pi over a x.
Yes.
But when we wrote n,
It's 2, so it's n is 2, okay? So I think it's okay. All right, so let's now state the problem. The problem will be that, okay, I'm going to put it perhaps over here. Let's see, maybe over here. Okay, so what I'm going to do is I'm going to say, given that at psi at x0 is equal to 1 over square root of 2 u1 of x plus u2 of x. Okay. let's find how the average value of x is changing with time. Okay? So in this case, for this problem, we have already solved the Schrödinger equation. We know the u1s and u2s and such things. And all we need to do is just apply the form going from the initial condition to the time-dependent form, and then just calculate what the x of t is. So if that's the case, okay, if psi x 0 is that quantity, I know that psi xt is going to be 1 over square root of 2, okay, u1 of x e to the minus I e1 t over h bar plus u2 e to the minus I e2 t over h bar. Okay, now I chose 1 over square root of 2 as the prefactor. Now just remember that last time we discussed, in order for this to be consistent with the probability description, the magnitude squares of those constants should add up to 1. Okay, so I can always check that the C1 magnitude squared plus C2 magnitude squared is equal to 1, because each one of these things is 1 over square root of 2, right? So this just checks out. So normalization condition is satisfied. Now I have this as my psi, which is changing with time. Okay, so I want to find out what the average value of x is with respect to this psi. So I'm going to write down psi star xt, x psi xt dx minus infinity to infinity. Okay, and that then tells me I'm going to get 1 over 2 an integral. Now all of these u's are defined between minus a over 2 and plus a over 2, and they are 0 otherwise. So my integral is really between minus a over 2 and plus a over 2, because outside that the u is 0. Okay, so I have 1 over 2 complex conjugate psi, so it's going to come in with u1 star. Okay, all of these are real functions, but just to make sure that we do everything formally, let's put them down. X, and then psi itself, u1 of x plus u2 of x dx. All right? Yes, very important. Thank you. So I'll put them down. Okay, sorry about that. Let me write that again. So I'm going to get u1 star e to the I e1 t over h bar plus u2 star e to the I e2 t over h bar, x, and then the function u1 e to the minus I e1 t over h bar plus u2 e to the minus I e2 t over h bar dx. Okay, so looks like a long integral, but remember that the integral is only over x, so I'm integrating over only these u1s. So there will be certain terms, certain cross terms, etc. But let's just look at them. For example, I'm going to get a term which looks like u1 star u1 x dx from minus a over 2 to a over 2. Okay, so there will be some term like this. Obviously, it will be multiplied by prefactors, etc. Okay, so the time dependence is still there. But I am now interested in this part of the integral. What do I get for that integral? So, okay, expectation of x for the first state. Okay, so it's 0, right? Because now I have chosen my origin to be at 0, which is going to make my life a little easier. Okay, so that's why we can shift our x-axis to a place which is more convenient for our algebra. So you could also say that these are real functions. u1 star is equal to u1. So you have this u1 squared, which is the square of the ground state function, which is even. So these two functions multiplied together is even. And then you have this x odd, so I'm going to get 0. All right? So what about, let's choose another term. Let's look at u2 star u2 minus a over 2 to a over 2 x dx. What do I get for this?
0 again.
0, right? Because this is now the expected value of x, okay, or the average value of x for the second state. But the second state is also symmetric, right? It is odd with respect to, okay, u1 is odd with respect to x equal to 0. But when I look at u2 star times u2, okay, the product is even. So again, I have the same argument. This product here is even, and I have an odd term here, so that's 0. So you see lots of terms are going to be 0. The only non-zero term is going to be something which mixes u1 and u2. Okay, so if I have now the integral minus a over 2 to a over 2 u1 star of x, well, u2 of x times x dx. Now, what does this look like? u1, so let me write down the functions, minus a over 2 to a over 2. u1, remember, is the cosine function, so it's cosine pi over ax. u2 is the sine function, so it's going to be sine 2 pi over ax, right? And then I also have the x and dx. Now you see cosine is the even function. Okay, sine is odd, but x is odd also. So this product together is even. So the integral as a whole is an even function. So it's going to get some finite result. Okay? So I'm not going to struggle with this integral. Okay, you can do it as an exercise. Let's just give it a name. Okay, let's call it I. Okay, so it's just going to have some value, and let's just use it. Okay, so let me now write down what this average value of x is going to be. Okay, so average value of x is equal to, there's a 1 over 2 and there are two terms that survive this product, right? You have u1 times u1 gives you 0, u2 times u2 gives you 0, but then you have u1 star u1 times x, which we called I. Hmm?
E minus E1 minus.
Okay, so we shouldn't forget the time dependence, which is why we are doing this actually. I to the E1 minus E2, E1 minus E2 T over H bar. And we have another integral, which is going to be U2 star U1,
This is also I.
which is also I, because U1 and U2 are real functions. So I'm going to get plus I e to the I E2 minus E1 times T over H bar. Okay. Now that I have these functions, okay, I can try to interpret what is going on here. Okay, so remember that I can write something, an exponential with a plus some argument and minus the same argument as e to the I something a plus e to the minus I a something is equal to what?
Cosine
Yeah, there's a factor 2 cosine a, right? So I already have a 1/2 here. So I'm going to get I, whatever that integral is, and doesn't really matter which one I choose here as the plus, and the other one is minus, because cosine is symmetric under a going to minus a. So I can choose the positive quantity, E2 minus E1 over H bar. Well, yeah, T over H bar, but I want to write the omega part separately. Okay, so cosine E2 minus E1 over H bar times T. Okay, so this is now, that means that my average value of x is oscillating with a frequency which is related to the energy difference. So if we just think about this now as a classical object with some position and oscillating like this, you see I have a charge inside this well. So I have this potential well, and I have chosen this point here. Okay, so this object is oscillating back and forth at this frequency, okay, a charged particle oscillating at that frequency inside the well. So it will couple to electromagnetic waves. If I have an electromagnetic wave which is oscillating at the same frequency, I can impart additional energy to it, or I can take out energy from the system. Okay? But what does that correspond to? You see, now if we think quantum mechanically, if there is some energy change, that means there is some, okay, possibility that the particle is going from the higher energy state to the lower energy state, in which case it goes from this state E2 to state E1, and the energy difference is h bar omega, okay, is going to be equal to E2 minus E1. So the omega, the oscillation frequency that is associated with the photon that's released, is equal to the frequency that I obtain here. And when I go through this semi-classical argument that, okay, there's this electromagnetic wave which is pushing and pulling the electron at exactly the same frequency as it wants to oscillate, okay, that's a resonance, right? That's how we work out resonance. If you put a child on a swing, okay, so we have this child, could be grown up, okay, swinging here. There's some natural frequency of oscillation in which that swing goes back and forth. And if we just supply force at the same frequency, it's a resonance, and you transfer energy to the system. Okay, so we pick up the basic points about the energy transfer to a particle inside a quantum state by looking at how the position is changing back and forth. Okay, so it looks like perhaps a dipole, because if it's negative, there's probably some positive charge sitting someplace fixed inside this well for charge neutrality. So together they form a dipole, and so you have a dipole which is oscillating back and forth, which couples to radiation. Okay, any questions? Any comments? Okay, so what I will do next is go to another Hamiltonian, another type of potential energy. Now I'll deviate a little from the sequence in your textbook from Griffiths. Griffiths continues on with various other bound states, but at this point I want to go to a scattering state, okay, so that we get some experience with continuous energy states also. All right. So let's analyze the free particle. So in the case of the free particle is very easy, right? There's no potential. So if there's no potential, the Hamiltonian is just the kinetic energy, p squared over 2m. And in terms of our operators, it turns into minus h bar squared over 2m del squared del x squared. Okay. So we'll follow this procedure that we already have on the board here. Okay, we are going to first solve the time-independent Schrödinger equation. What is the time-independent Schrödinger equation? Okay, time-independent Schrödinger equation will be okay, h psi equals e psi, and I'm going to get minus h bar squared over 2m, ordinary derivative because I have factored out the time, I have separated out the time, times, okay, so these were really u's, right? U is equal to E times U. So this is an easy equation to solve. D squared dx squared U is equal to minus 2me over h bar squared U, right? So what do the solutions look like? Second derivative of a function is equal to minus a constant, okay, times u. What type of exponential? Okay, complex exponential, so they will be periodic functions. So the solution is that I'm going to get u of x is equal to okay, linear combinations of, because there are two solutions, e to the I square root of, let me just put a k instead of struggling with that. Let me just say this is e to the I kx or e to the minus I kx, but I have to make sure that k squared is equal to minus 2m, not, no, just plus 2me over h bar squared. Okay? So I'm going to get a form like this with k equal to that. Okay, because when I differentiate twice with respect to k, it's going to bring down a k squared, a minus k squared. So the k squared part must be equal to 2me over h bar squared. Okay? Now, let's just see what this is saying. Let's look at what k is. K is going to be equal to square root of 2me over h bar, or h bar times k is equal to square root of 2me. Now remember that the energy, I have only kinetic energy in this problem, and energy itself is equal to p squared over 2m. So since I have p squared over 2m, okay, if I put p squared over 2m here, you see 2m's cancel, and then I get square root of p squared, which is just p. Okay, so h bar k is the momentum of the particle. And that makes sense because in this system, momentum is conserved. There's no potential. Okay, if I have a constant energy, which it means it corresponds to a constant momentum. Okay. All right, so this is my stationary state for a certain energy. Now, one point that perhaps I'll state here, you see that for the same energy value, I have two possible momentum values. That's because energy is p squared over 2m. So for the same energy, I have two possible momentum states, one going in the plus x direction, the other one going in the minus x direction. So two different states have the same energy. That is called degeneracy. Okay, so new terminology. Okay, two states, actual two or more states, but in this case I have just two. Two states have the same energy. Okay, so instead of labeling these states in terms of energy, it's better to label them in terms of k, because k is related to momentum. Yes?
Professor, might be, but the previous topic, we take Fourier series, right, for the function, but however, for the special case for infinite squares, sometimes the square is between the, as the example, minus a divided by 2 and plus a divided by 2.
Yes.
So basic just sine and sine or cosine, not approximation, sine and cosine application.
Excuse me.
Might not work. So can we, but if we, whatever the function is, if we shift this function between minus a2 to plus a2 to at the magnitude of a2 to the left, we end up with 0 and a, right? So at that point we can evaluate them as an even or odd function. So can we do a Fourier series at the coordinate system of x minus or plus a divided by 2 instead of normal coordinate system, because if we are between minus a2 and plus a2 at the at the normal coordinate system, maybe Fourier series is a little bit harder.
Okay, you can choose your coordinate axes in any way that will make your computations much easier. Now, for the Fourier series part, the Fourier series works no matter where you put your x-axis. Okay, it would be a disaster if it depended on where you put your x-axis. So let me just squeeze it over here. You can have a problem if it's going to be convenient for you, in which your square well is between some value b and a plus b. Okay, so again, the width of the well is a. Okay, and you are going to get eigenfunctions here which go like this, and they'll be orthogonal to one another. Okay. Mathematically, there's no difference between these when they appear here and when they appear there. So orthogonality doesn't change. Your integrals will change, obviously, the limits and everything, but the various stationary states will still be orthogonal to one another. It's just that you may prefer to do these integrals rather than the others. Okay, it depends on your problem. Most usually, the choice will be either between 0 and a or minus a over 2 and a, just because of convenience. But you can choose it anywhere you like. Okay, it will work anywhere. Okay, so we have these states. So what I'm going to do is I'm going to call these things u sub k of x. Okay, now going back to our general description here, when we had two different objects here, okay, where we just used the fact that they formed an orthonormal set. So remember that I told you last time that if you have two of these things, we call them un and m, but doesn't matter, ue of x star and u e prime of x integrated dx was delta e prime for discrete energies e and e prime. Now we have here something which is not discrete. It forms a continuum. You have a value k which can be anything you like, because energy has to be positive, otherwise you can't even evaluate the square root. The energy has to be positive, but k itself can be, okay, a continuous variable, either from 0 to infinity or 0 to minus infinity. Okay, so I can no longer use this type of orthogonality directly. But what I can do, which is very convenient, is to use a different type of orthogonality. Maybe I'll move here. What I will do is I'll take two of these functions. So something which is uk is going to be some normalization constant, let me just call it a, times e to the I kx, right? And we discussed this problem before. We cannot use this a to normalize the total wave function, because the total wave function now extends from minus infinity to plus infinity. And we interpreted it to be being related to the probability current. But now we are going to actually give this thing a value so that it is properly normalized in order to satisfy some orthogonality. Okay, so if I have some other function, k prime, okay, that is going to have the form I k prime x. Okay. Now, I'm going to go through the same process. What will I get when I get uk, say, star of x, uk prime of x dx minus infinity to infinity? I'm going to get a star a, an integral minus infinity to infinity. So this will look like e to the I k prime minus k times x dx. And what is that integral?
Is k the multiple of delta function? Is k the multiple of delta function?
Okay, it's the Dirac delta function. Are you familiar with this? Yes? Yes or no?
Yes.
Some yeses, some nos. Okay. Well, okay. Let me just first write it down and then we'll discuss it. This is going to be 2 pi times delta k minus k prime. Okay, so if I want to then normalize this thing properly, I don't want this factor 2 pi. So what I do is I choose a to be real and positive, and I choose a to be 1 over square root of 2 pi. Okay, so let me just write down my uk now. uk sub x is 1 over square root of 2 pi e to the I k x. It corresponds to a particle with a definite momentum, okay, which is equal to k times h bar, and energy p squared over 2m. All right, so these are now my eigenstates. For the delta function, okay, if you have not seen it before, you can obtain it by, well, careful, Fourier transformation. Okay, you can prove certain points of Fourier transformation by using this identity. So if you trust Fourier transform more than mathematics, you can derive this that way. But obviously you have to, okay, let me just squeeze very little algebra here for those of you who have not seen this before. If you look at an integral which has the form minus infinity to infinity e to the I k x, for example, dx, and x, let's see, let's put it minus I epsilon. Okay, so suppose I have an integral like this. Do you know how to evaluate such an integral? Using complex
Residues.
Yes, using residues. Okay, but do you know how to do this with residues if you are not a mathematics major? You have not seen residues in math? Okay, well, let me just go through it and maybe you'll remember it as we go along. So this is a nice analytic function, except that it has a it has been divided by this factor here, so it has a pole. Okay, you have something like this. This is the real axis. This is the imaginary x-axis. Okay, and the pole is here at I epsilon near the origin, and you are integrating this. Let's put a nice red integral sign, okay, along the real x-axis from minus infinity to plus infinity. Now, the nice thing about these complex integrations is that if we can form this into a contour, yes, into a closed loop, then you have the result. Okay? But you have to do it carefully because if you try to close it like this, okay, actually there are two ways you can close it, either like this or like that. Okay, you have to make sure that this part that you are adding to the integral, that curved part, gives you no contribution. Okay, so over here, if you look at what you have very large values of x with a positive imaginary part. Okay, so multiplied by I, it's going to be a minus very large number. So on this part of the loop, this goes to 0 if x is greater than 0. But if x is less than 0, then it's the opposite. Then this piece goes to 0 if x is less than 0. So you are allowed to complete this into a loop this way if x is greater than 0, this way if x is less than 0. And then, since it's a loop, you get the value of the residue. So you are going to get what? 2 pi I times, okay? So I'm going to put in I epsilon into e to the I k x, e to the k I k I epsilon, right? If x is greater than 0.
You mean k?
Yes, I mean k. I'm sorry, it's also true here. If k is greater than 0. So, okay, and 0 otherwise. Okay, and as epsilon goes to 0, this thing goes to 1, so you end up with 2 pi I. So you get something which looks like this as a function of k. So this integral is equal to 0 if k is less than 0, but it's equal to 2 pi I if k is greater than 0. So now if I differentiate this, derivative of this is going to give me what? 2 pi I times delta k. So I have to do the same thing to the integral. So that's going to give me integral, okay, differentiating with respect to k. It's going to bring down an I x e to the I k x divided by k minus I epsilon. Okay, you can cancel the i's. And in the limit epsilon goes to 0, this piece cancels that piece. Okay, not really. One of them is a pole, but again, trust me type of thing. Okay, so you get e to the I k x integrated gives you 2 pi times a delta function.
This is respect to k, right?
No, again x. Okay, because so that the result depends on k.
I
Yes.
don't understand the last part. I understand this integral equal to this, but
Okay, if you just differentiate this is a delta function, right?
yes.
Okay, it's 2 pi I times delta function. Now, I am differentiating the result, so I should differentiate the integral also. So if I differentiate this with respect to k, just like I did for this, it brings down an ix. Okay? So it's going to be ix times e to the I k x divided by x minus ie. Okay? And then as epsilon goes to 0, you get just this integral. Okay? All right, how are we doing on time? Not very well. Okay, let's have our break, then we'll go.